Okay, so we're going to talk about the next part of this talk, which is carrier acquisition. So what carrier acquisition means specifically is that you are generating a synchronized carrier on the receiver end. So that's what carrier acquisition means. So that'll actually perform matching between what's, the input and then the output. So this is actually done on the receiver side. Okay? And then once we cover this, should be about maybe half an hour or so, and then I'll take a break again just to give you guys a little bit of a breather, and then we'll do the tutorial. Okay? Okay, so how do we demodulate? So when you have modulated signals such as AM, or there might be single sideband with the carrier or vestigial sideband with the carrier, but when you demodulate and there's a carrier built into the actual modulated signal, there's two ways you can demodulate. So the first way, which you already know, is what's known as envelope detection. That assumes that the envelope doesn't cross the horizontal axis. And then if it does, then you have the next technique, which is coherent detection, which is what I talked about, where you have a carrier on the receiver end, or sorry, there's a cosine on the receiver end, and then you do a multiplication and then a low-pass filter. So with suppressed carrier modulated signals, as I talked about, so double sideband suppressed carrier, also a single sideband or vestigial sideband by themselves without a carrier do require coherence. So there's no envelope detector you can use to demodulate these signals. So unless you have a carrier on top, you're going to have to use coherent detection, unfortunately. So for coherent or synchronous detection, we have to generate a local carrier. That's what we already know at the receiver. Okay, so if there is any discrepancy, so if you have a carrier frequency that's coming in, and then if on the receiver end, if you have that carrier where if it's mismatched in phase or if it's mismatched in frequency, then we've already discussed this, a couple of classes ago, where you're not going to get a nice output. So there's going to be, there might be some I guess, not noise, but there might be some residual components, and the actual original message might be scaled down by a little bit, depending on whatever phase is introduced or phase difference between the carrier that's coming in and the receiving, the receiver local carrier. Where are we? Here we go. Okay. So carrier acquisition is basically generating a local carrier at the receiver such that the carrier frequency that's coming in and the local carrier that is generated, they both match in frequency and in phase. Okay? So that's what that exactly means. So you're generating a local carrier that is frequency and phase synchronized from the transmitted signal. So that's the point of doing carrier acquisition. Okay? So here's an alternative, all right? So remember that when you're doing double sideband suppressed carrier, you're transmitting your signal without a carrier. So what you can do here is that you can perform, I guess, a kind of semi-working amplitude modulation, or DSB-LC, where you would generate or you produce a carrier signal, but the power or the amplitude is going to be very, very, very small, so that it doesn't affect any of the electronics. So you're going to add a separate carrier to the modulated signal at a reduced level. So remember what the spectrum looks like. So you have your message that is, plus minus whatever the carrier frequency is, and you have an impulse that is centered at your carrier frequency. But you make the height of that impulse as small as possible so that it looks like double sideband suppressed carrier, but it's actually amplitude modulation instead. Okay? So it converts the suppressed carrier signal into a small carrier format. So this is basically AM, but the carrier is very small. Okay? So obviously you're going to need, at the receiver end, you're going to still need some electronics or some signal processing concepts to be able to lock on and track the carrier. Okay, so what's happening here, is that we can actually extract out what the actual carrier would be, as we talked about in phase lock loops, and we can use that to perform demodulation. So where this is, I guess, another way to do exactly that same step. Okay, so remember what I talked about in terms of phase lock loops. So we can use this to determine what the carrier frequency is that's coming in. So you're generating in this case, remember this is a 90-degree phase shift. So the output of the voltage controlled oscillator will give you a frequency or give you a sinusoid or a periodic waveform that matches the input carrier frequency. Okay, so remember this is used for demodulating AM signals for coherent detection, so that's when the envelope goes below the horizontal axis. You can also use it for demodulating FM and PN signals if you wish. So there's two different applications, but the point is to generate a carrier such that it matches an input frequency, with respect to the, it matches the input carrier frequency. So, okay, So let's talk about demodulating double sideband suppressed carrier signal. So we're going to perform carrier acquisition, or generating a carrier on the receiver end that matches the frequencies from the whatever, that matches the carrier frequency that's coming into the input. So if you recall, a double sideband suppressed carrier modulated signal is simply taking your message and multiplying by cos. We already know that, okay? And when you actually take a look in terms of the the frequency spectrum, we notice that there is no carrier term. That is suppressed. So you actually do not see the carrier in the transform. Okay. So if you actually do a little bit of math, or if you have some extra components, what you can actually do is you're able to extract out the carrier inside that suppressed carrier signal so that you can use that and demodulate the output. So remember, what suppressed means is that the output, you actually do not see the actual carrier signal. But if you actually introduce a couple of electronics and do a little bit of smart math, you can actually extract out what that actual carrier was to begin with, and you can use that to demodulate your signal. So we can actually unsuppress that carrier, extract it out, get what the actual carrier is, then we can actually use that and multiply it with our input signal that's coming in, because both the carrier that you extract out and the modulated signal will actually match in terms of the frequencies, right? They'll exactly match. Okay? With the help of trig identities and some clever signal processing, we may still be able to generate a phase and frequency coherent carrier from the received waveform with the receiver. So that's what I just talked about earlier. Okay, so what we're going to do is I'm going to introduce two different notations here. So we're going to assume that the message is zero mean. So what that means is that the DC offset is zero. So whenever you take a look at the DC offset of an AC waveform, right, the DC offset is basically the average value, if you remember from electronics, right? So the DC offset, or the DC level, is the average value. Okay, so that's what you need to know. So what we can do here is, let's for a moment assume that if we decide to square the signal, the mean is no longer equal to zero, which actually makes sense, right? Because if you had a sinusoid, usually, if you integrate over one period, the mean is actually zero. But if you actually square that signal and try to figure out what the average is no longer zero, because all the components are positive now, so you're going to actually get a positive average. Okay? So we're going to square the signal, and you actually get a non-zero mean. So what we can actually do is we can split this up so that we have the zero mean signal of the squared, and then you add a DC level on top, which actually makes sense, right? Because this here is the m squared of t with zero mean, or the DC is zero. Okay, so if I have this signal where it's squared and then I remove the DC level, it would be the same thing as just taking the signal and adding a DC offset to produce the same thing, right? So if I were to take the signal and add it with the DC level, you're actually getting the same thing, because remember, the DC level is just simply an average value, it's just a bias. So if I were to take my signal, remove the bias, I have some signal that's fluctuating around zero, and then if I add a DC offset to it, I would get the original signal back. So let's just assume that we can break this up so that we have a composition of a DC offset plus the equivalent signal that is squared without any DC offset to it. So if you add them both together, you actually get the original signal. Okay, so what we're going to do is, so we have our double sideband suppressed carrier signal coming in, and let's say we have some sort of nonlinear device that actually squares the signal coming in. So this is a nonlinear device. Nonlinear device that'll actually square the signal that's coming in. So remember, this is m of t cos. Okay, if I square it, I should get that, which actually makes sense, right? When you have a times b squared, it's the same thing as a squared b squared, and that's what we get. Simple, simple math rules here. Okay. So remember that we have a formula where cosine squared of x is equal to what? A half plus a half cos 2x, okay? And this decomposition breaks down into this and that. That's pretty standard, all right? And then also, because m squared of t factors into this, you will get this as the output, which is standard. We already know about this. Okay, but notice that we have m squared now instead of just m by itself. Okay, and if you remember, we can represent m of squared, right, as some DC level plus the zero mean version of the squared term. So that substitution is made over here. Okay? Okay, so now we have that. Let's go ahead and expand it out a little bit. So we can see here that this cosine, sorry, what's going on here? Here. So we can expand this out, right? So this cosine gets factored into, not factored in, but expanded out, and then we have two separate terms, 1 and 2. All right, well, that makes sense. So we square it first, and then what we're going to do now is we're going to apply a bandpass filter. Okay, we're going to go ahead and apply a bandpass filter. So when you have a bandpass filter, what we're going to do specifically is we're going to detect, let's see here, let me just scroll through and figure out what's going on here. Yes, okay, that's fine, that's good. Yeah, okay. Okay, so we're going to have some sort of bandpass filter, all right, so that we can filter out anything that is within a certain range, right? So we apply a bandpass, let's apply a bandpass filter to the output right now. So what you have here, so this is, at this point, we have this output which we've already discovered. And then what we're going to do is we're going to take this and we're going to put a bandpass filter to it. So remember, you're just convolving with whatever the impulse response is, which is just multiplication of frequency domain. So when we actually put this through a bandpass filter, okay, so this is what we actually get. Okay, so the green here is what the spectrum would look like for m squared. And if you take a look at what the bandwidth is, you'll see that it's twice the bandwidth. Because remember, if you remember from the first tutorial question, the first tutorial, if you were to square an input signal, the frequency domain, you're basically just adding the bandwidth by twice, right? Because you can think of this as m squared of t. It's just, you're just multiplying these two signals together, right? And then when you're doing the frequency domain, when you actually take a look at this in terms of frequency, you're just convolving these two together. Right? And then if you remember the property, if you have two finite length signals and if you convolve them together, the output is basically the output width is just the sum of the two. Okay? So the bandwidth is just b of m plus b of m, which is twice as much, which is why you get twice as much here. So when you square a signal, the output bandwidth would just be adding the message signal twice, the message signal bandwidth. That's why you see twice the bandwidth here. Okay? So this is what the spectrum looks like. And then we have so when you actually take the Fourier transform of this, you're going to have two impulses at plus minus 2fc. And then we're only considering the positive here. The negative we're going to assume is symmetric, so positive only. Okay? And then this is what the spectrum looks like. This is the zero mean signal. So when you have zero mean, that means your DC offset is 0. So the Fourier transform component at 0 hertz is going to be 0. That's why there's a dip over here. So this is what the spectrum would possibly look like. That is zero means, and then you just have an impulse there. Okay, so if I apply a bandpass filter to this, okay, what I want to do is I want to do it in such a way where I want to make the bandpass filter, the bandwidth to be very narrow, so that I get rid of the green component, which is the original 1 squared, and then the blue sidebands as well. I want to just isolate the red component by itself so that I can use this as a carrier and demodulate my signal. Okay, so I want to make this so this bandpass filter is narrow enough to isolate, carrier and filter everything else out. Yes?
Half k equals to omega c. How do you know it's a delta function?
Okay. What is the Fourier transform for cosine? What is the transform? What is it? It's half delta. Not delta, but it's f. Okay, plus half delta f plus. Okay, so there's two impulses here. Yeah. And that's why you have one impulse here. In this case, it's f of c. Sorry?
Half x pi t.
Oh, well, this is just DSB-SC, no? Right? So you can think of this as m, and this is cos of 2 omega ct. Right? Right, so this here is your message signal. So this is just double sideband suppressed carrier. So we know that it will take two copies, one at 2fc and one at minus 2fc. Okay, so this is just double sideband suppressed carrier, right? So I want to design a filter that is narrow enough so that I want to isolate out this carrier and filter everything else out. And the reason why I'm doing this is because, well, I've effectively extracted out the carrier component of my double sideband suppressed carrier. So I've actually unsuppressed it out. So now I can use this carrier and multiply it with my DSB-SC signal, because now you have your modulated wave and the carrier, both of them would be in sync, right? Because what you're doing is you are doing it in parallel, where you have a double sideband suppressed carrier coming in, and then you take a branch, you put it through a squaring and a bandpass filter so that you actually get the actual carrier. So then both of those signals are in sync, you multiply them out, and then they're finally in sync, okay? Okay, so that's fine, yep. Okay, so yeah, I guess this is important. So if usually there might be some sort of small residual, because this is because we want to have a non-ideal bandpass filter. We want to have a realizable one. Okay, so what I talked about previously was assuming an ideal bandpass filter. That's actually not, possible. So you have to make the bandpass filter in such a way where the transition band is going to be very small. So when you actually do that, if you add, you'll have a small residual at the output, and if you add this with your, with your carrier, then it's going to be approximately the same. Okay. Okay. So once we have this here, then what we can do now is, let's see, what can we do now? So yes. So what you can do here is that you will have a phase lock loop, right? That'll be tuned to 2FC, right? So the phase lock loop is here so that it adjusts for any tolerances. So remember, so this voltage controlled output, so the F of 0 would basically be twice the twice the carrier frequency, because that's what we're trying to extract out, right? So when you have the your ideal bandpass, your non-ideal bandpass filter, there might be some a little tolerances, or might be some frequency changes, might be some errors. So you put an additional phase lock loop here to make sure that the output will be twice the carrier frequency. Okay, so then this will be sine, and then you'll have to do another phase shift to get your cos. So at this point here, we know this already. Okay, at this output, we have the carrier frequency approximately once you apply a bandpass filter. Then you put it through a phase lock loop, make sure that you're tuning this so that it's at the exact frequency with respect to the carrier. So then you get, remember, this does a phase shift of 90 degrees, so you get a sine, and then you probably want to do an additional phase shift to get it to be cos so you can demodulate. And here we go. Okay, so this, I don't know why that's a divide, this should be a multiply. Okay, so you do a phase shifter, and then what you're doing here is you're multiplying by 2 so that you get rid of these constants. Okay, so you get rid of this constant. So you multiply by 2, so then you get this cosine wave. And then now what you do here is you use this to a coherent demodulator. So you have M of t coming in, and then you also have M of t cosine omega t over here. So how it works is you take this, okay, and then you take this guy, multiply this, you get a low pass filter, and then you get M of t as the output. So that's what it means by two coherent demodulator. So what you're doing here, the whole point of this is to extract out what the original carrier was to some constant. You take this, you multiply it with your DSB-SC signal, you apply a low pass filter, and then you finally get your message signal. So that's the whole point here, is to actually extract out the carrier from what was suppressed from the beginning. So apply a squaring function, do a bandpass filter, get a phase lock loop in there to make sure that you actually will ensure that your carrier frequencies match, even though there might be a little bit of some tolerances or some errors. You'll do a phase shift to get cos, and then you want to multiply by 2 to get rid of these gains of a half here. And there you go. Okay? And that would be one way to demodulate a double sideband suppressed carrier signal. So here's another way you can do it. This is the last application I have, and then I'll take a break and we'll do the tutorial. Okay? So you can actually perform what's known as a Costas loop. So Costas was the engineer who actually designed doing the coherent demodulation by carrier acquisition in this way. Okay? So let's break this up very slowly. So we have some message signal that's coming in. So this was double sideband suppressed carrier. Okay, but there is some desired frequency. This is the carrier frequency. And there might be some additional random phase. So this is random. We actually don't know for sure what it is. So ideally, we like it to be 0, but it may not be the case. Okay? So the whole point of this is that you have a voltage-controlled oscillator here such that it will make sure that when you perform coherent demodulation, the frequencies do match up. So let's actually go through this block diagram slowly to figure out how this will actually perform demodulation coherently. Okay? All right, so let's actually start with this branch here. So we have so this is your DSB-SC signal. Okay, it's coming in. and then we have two carriers. Okay, so one is generated by a cosine wave, right? In this case, you don't need to phase shift. This is not a phase lock loop, so this will just generate a cosine wave. This is not a phase lock loop anymore. This is just a random, this is just a standard voltage controlled oscillator that is generating some cosine wave. So we have a voltage controlled oscillator that generates a carrier frequency that, you have to make sure that they match, right, or roughly the same. Okay, and then we have a phase shifter that will generate a sinusoidal equivalent. Okay, so at this point here, we're going to take our signal, and then we also multiply by 2. The reason why is because it's for notational convenience, because when you take a product of two cosines, you have a half, and then the half and the multiplication by 2 will cancel it out. So the 2 is mainly there for convenience. So this is for convenience. Okay, so when you multiply these two things together, you can actually use the trigonometric identity, which will split them up. Okay, so you actually get this and this. And then when you apply a low-pass filter, what will happen is that this component, this second component, will disappear, because that's what the low-pass filter will do. So the output you get is just some constant factor that is taking a look at the difference between the phase of the input and the phase of the voltage control oscillator that's multiplied by your message. So that's what we get after. So, okay. So this gets filtered out, and then this is what we get here. And then what we'll do is we'll represent this. We'll call this theta sub e, which is the error in phase. Okay, so that's what we're going to change this as. So once you multiply this by two cosines, and then cosines of different phases but match the same carrier frequencies, and you apply a low-pass filter, you get this signal. You get this instead. So it's your message multiplied by some non-zero factor. Okay. If the error is equal to 0, then all you're getting is the original message, which is nice. If the error was very large, then the output is going to decrease, and you won't get the original message anymore. But we'll talk about that soon. Okay, so this here, this is what the output would be, which is what I just talked about. All right, so let's take a look at the bottom branch. So you have cos, and then you have two sine coming in, right? And then you have a product of cos and sine, and then you can use the product formulas to be able to split it up into two sinusoids. Okay, so you have this guy here. So you're just taking, it's sine A plus sine B and sine A minus sine B, right? So when you do this, you apply a low-pass filter, you get rid of this is basically just, double sideband suppressed carrier modulation. You're going plus minus 2 FC, and then this gets filtered out because of the low-pass filter. So all you're left with is this guy over here, okay? And that's what the output would be, okay? So here, we have two branches here. So we have cos and sine, and then we're going to multiply these together. And then when you multiply these out, you get m. So you have m of cos, okay, times m of sine, okay? And then these two get multiplied together, so you get m squared, and then the cos and the sine are here. That's nice. And then remember, there's a property where it's, let me see here, sine of 2x is equal to 2 sine x cos, yeah? So if I divide by 2 on both sides, I get half sine 2x equals sine and then cos. So I can represent this as half sine 2 of theta sub e, which is what is happening over here. Okay, so then how does this work? What is this actually, what's the point of doing this? Well, if you apply a low-pass filter to this output, right, what will happen here is that it will, let's see what's going on here. So, okay, so what's happening here is, remember that m squared of t was equal to some, bias plus the zero mean version. Okay, and then we can replace this with this over here, which we get over here. Okay, so that's what's happening here. Oops. Okay. So now what's going on here is that when we apply a low-pass filter, okay, narrow band, what this means is that we will make it so that this term actually goes away, right? So what's happening here is you're basically doing a modulation with respect to theta e, right? So when you're doing a low-pass filter, this term goes away, so you're left with this. So what this is telling us here is that the error is directly proportional to the phase error between the output, which is the, the voltage controlled oscillator output, and the input that's coming in terms of the phase. Okay, so, So here's a little bit of notational convenience here. So if theta E is very small, if theta E is very small, this means that sine of theta E is approximately theta E. So if it's very, very small, if theta E is very small, then what's going to happen is that there's a limited range where it's actually linear. So this is actually, so it's approximately linear. So if your values are sufficiently small enough, then if you take the sine of that number, it's going to approximately be just linear. So sine of 0.0001 is going to be approximately 0.0001. So that's what's going on here. So this is saying that it's approximately linear. Oopsie. Okay. So then what's the point of this? So this means that if it's very small, this means that it's just directly proportional to the phase itself. So this is assuming that the error is very small. Okay. So what does that actually mean? So what this is saying to us now is that if the error is very small, that means that the voltage-controlled oscillator, the voltage should not change. So how this works now is that, remember, this will give you a error signal where it actually determines what the carrier frequency is going to be. So if the error signal is very small, right? So remember what the output is. This is m of t cos, right? So if theta E approaches 0, that means that the output will equal m of t, okay? Because cos of 0 is equal to 1. So then when the error signal is equal to 0, this means that here, if you take a look between here and here, right? If the error signal is so as this approaches 0, that means the carrier frequencies, they match. And that's what you want, okay? So if the error signal is very large, this means that there will be a large error, so that means that the voltage-controlled oscillator has to change the frequency so that it matches the original input. So that's what you get here. So as long as the error signal is very small, you will get the original message right here, right? And then if it's not, if it's large, then the voltage-controlled oscillator will change it so that the carrier frequencies match, so the error is finally driven down towards 0. Okay. So here we go here. So this is just summarizing what I talked about before. So based on the preceding analysis, which I talked about, we generate a feedback system where the voltage-controlled input is simply the error signal is coming in, which is the difference between the phase. So we have some sort of phase here between, that's generated by the voltage-controlled oscillator, and we also have some input phase going in. So as long as both the phases match, then we shouldn't have to generate error signal. Oh, sorry, the error signal is 0, so that the frequency should actually match. So the voltage-controlled output, it changes to drive the error signal down to 0. So as the error signal approaches 0, this means that the output and input phases, they match, and you will finally get a message signal that will, then you'll finally get a message signal that's expected. Okay, so that's all I have today for theory. I'm going to take another break, about 10 minutes. We come back, I'll do some questions, and hopefully we'll get out of here by 8:15, 8:25 tops. Okay, thanks.